All right, this 2016 number 5. We should be excited to see these graphs where you've got concentration versus time and natural log concentration and reciprocal concentration. Those are graphs that we should be comfortable with. This gives us a little equation. It's an integrated rate law when you see those graphs, which means we're isolating one reactant. And it only happens to be one reactant in this equation, which is nice. It says high temperatures, this thing reacts according to the equation above. The rate of the reaction was studied at 625 Kelvin. Perfect. 2 different trials, each with different starting concentrations carried out, and they plotted these 3 different ways. Super. Concentration versus time. If this was linear, which it's not, that would be 0 order. So this is not a 0 order reaction. The second one, if this was linear, which it is not, natural log of concentration versus time would be first order. And then the last one, if it was linear, which it is, the reciprocal of concentration versus time means that this is a second order reaction. And somewhere they're going to ask you if it's second order or what order it's in. It's like a free point. So make sure you get a hold of that guy. Good? And then here we go. It says for trial 1, calculate the initial pressure in atmospheres in the vessel at 625 Kelvin. Assume that initially all the gas present in the vessel is C4H6. We're looking for a pressure and they give us a temperature, and we're already on guard, not having any idea what's going to be on the exam this year, especially with the weirdness of this coronavirus. You're still going to have PV equals nRT. I would be shocked if you didn't. You're probably also going to have Q equals MCAT. I would be very surprised if you didn't. But PV equals nRT is one of those things we're looking for. We got a pressure, or we're asked for a pressure here, and they give us a temperature. That's my go-to. I'm going to here, and then I'm going to see if I can't figure out what the rest of those values are. Good? And so when I look at this, it wants the initial pressure is what the question says. And so I have initial concentration here in the first graph. For trial 1, they want trial 1. For trial 1, there is my initial concentration, 0.020. What is 0.020? That is molarity, or moles of that, divided by how many liters? Divided by 1 liter of that. And now I'm in business. I have a temperature, a volume, and a number of moles for this thing, and I can find pressure. So that's it. We're looking for pressure here. So pressure is going to be our question mark. We got a volume of 1 liter. Our moles value we just found, 0.020. We need to find this on the graph. That's moles of the initial reactant. They said it's all C4H6. I'm going to write the unit because I can. Times the R. They said they want the pressure in atmospheres. They're usually going to assign a unit to you because they don't want to look at a bunch of different answers. And so the pressure in atmospheres, our universal gas constant, 0.0821 liters times atmospheres over moles times Kelvin. I tell my students always PV equals nRT in atmospheres. That will save you from having to think too much there. Times the temperature that they gave us. They gave it to us in Kelvin, which is nice, 625 Kelvin. And we are going to calculate the pressure of that gas. The pressure of that gas equals 1.03 atmospheres of pressure. 3 sig figs. That's it. That's just about recognizing that being the starting concentration. Good? That's part A. Part B, you get 2 points, by the way, for part A. The setup gives you a point, and then a point for your correct answer. B on this problem says, use the data plotted in the graphs to determine the order of the reaction with respect to C4H6. It doesn't even ask you to explain it here. And so all you have to do is put second order. I think it's important you understand it's second order because plot of 1 over concentration of C4H6 is linear. I'm surprised it doesn't say explain that. That's your explanation for that in that problem. That's it on that one. If you're looking for the linear graph. And then the last one says the initial rate of reaction trial 1 is 0.001. Calculate the rate constant for the reaction at 625 Kelvin. So we've got to set up the rate expression. Rate equals little k, baby k, the rate constant, times the concentration of that thing, C4H6. And we already figured out it's second order, so that value will be squared. And they gave us all the other values we needed. The rate, 0.0010. That's molarities per second, equals the constant that we're trying to find, times the initial concentration here, 0.020 squared. Don't forget that it's second order there. Generic equation with the numbers in it, and then we can solve for K. And when we solve for K, we get 2.5. I'm surprised it doesn't say make sure you have a unit. You have to have a unit here on the 2.5 for K. They don't give you credit if there's no unit here. I'm assuming they don't give you credit anyway if there's no unit here. You need a unit. And so 2.5, what we do is we look at the order there. I stole this from Renee McCormick years ago. 2 fingers for the overall order, and then we take one of those away. That's how many molarities go on the bottom of this fraction. So it's a number over that number of molarities times the time unit. In this case, the time unit is seconds, and that's our rate constant value. Thank you, Renee McCormick. That's it. That's number 5. 7 minutes. It's supposed to take us about 7 minutes.